Which of the following are word problems for 1/2 times 1/3 and which are not? Explain your answer in each case. A, 1/3 of the children in the class have black hair. 1/2 have curly hair. How many children in the class have curly black hair? We can't actually answer this question. For all we know, we have the class and we could have, in terms of thirds and halves, right? We could have 1/2 of the class having curly hair. So 3, right? So that's half in an unconventional way. And we could have the third with black hair, which now I see I should have shaded with black, in these two squares here. So there could be absolutely no overlap. There could be no children in the class with curly black hair. So this is a possible picture for A. It's not guaranteed to be the answer for A, but that's the problem. We don't have enough information. So here we have a no, and it could possibly be let's see, do I know how to spell possibly? Right, it could be that for all we know. In B, we have that 1/3 of the children in the class have black hair. 1/2 of the children who have black hair also have curly hair. So let's draw an image for B. So we were told, well, the class grew a little, but that's my class. And we were told that 1/3 of the students have black hair. And well, let me label that. And half of those also had curly hair. So we do have a quantity of half of 1/3, but then they ask us how many children in the class have curly black hair. We don't know how many children. We know what fraction of children. So looking at part B, we've got 1/3 of, or part C, sorry, 1/3 of the children in a class have black hair. Check, check. Image for B. 1/2 of the children who have black hair also have curly hair. Same image. So C and B both have this image. But this time around, they're asking us what fraction of the children in the class have curly black hair. This one's finally a yes. So here we have a no because we don't know how many. 2? I don't know. Right? Okay. And in C, we have a yes because our beginning quantity was 1/3. And then we took 1/2 of 1/3, right? So we have shaded, double shaded here, 1/2 of our yellow block, which is 1/3 of the class, right? So this is a yes. This is 1/2 times 1/3. Now we have 1/3 of the children in the class have black hair. 1/2 of the children in the class have curly hair. What fraction of the children in the class have curly black hair? So we have the same issue in D that we had in A. It just further illustrates that there were two issues with A. And I saw that when they asked us how many children, when they asked us that in B, right? So part of our answer for A would be, we don't know how many children, but also we can't solve it through 1/2 times 1/3 anyway. So for D, we're also going to say no, because the image for D matches the image for A, in that it could possibly have no overlap in these children. There is enough in the half that's not having, oh, I guess we look at the third first. So when we look at the third, we have enough space in the other 2/3 to have half of the children in the class with curly hair and none of them have black hair, right? As our image in part A. So no for that one, because it's possibly that first image. So it could be 1/2 plus 1/3, but it's not 1/2 times 1/3, right? And even though A could be this image, the further issue is we don't know how many children there are. So having that as part of our question makes an issue for us. Don't know. Don't know, right? But the how many or what fraction, that's a good way to phrase it when all you know is fractions, right? Okay, so the only one was C. But it's important to explain each as a yes or a no, what it could be and what it isn't. Consider this word problem about baking brownies. You are baking brownies for your class. You put white frosting on 1/3 of the brownies, and you put small red hearts on 1/4 of the brownies. How many brownies have both white frosting and small red hearts on them? Can the brownie problem be solved? If so, solve the problem. If not, explain why. And then, is this 1/4 times 1/3? Is this 1/3 plus 1/4? And it is neither. It could be either. It's not clear. If could be that we frosted a third of the cake, right? Oh, brownies, sorry. So in terms of cutting our, let's label it. So here we have our brownies. And then we're going to frost a third. So let's get our frosting out. So I'm going to frost a third. Okay. And we're going to put little red hearts on a fourth of the brownies, right? But for all we know, the fourth of the brownies is on a whole different corner, right? Like we don't really know. And so for all we know, all of the hearts are in this corner. So here we have hearts on 1/4 of the brownie, right? And it isn't clear if it is this image, which is 1/3 plus 1/4. It is not clear if there was overlap either. So for part C, we would need this image. And for part B, we would want to frost a third of our brownies. So let's get our brownies frosted. And then put hearts on a fourth of the frosted. Then we would know what amount of brownies is heart covered and frosted, right? So let's label this 1/4 of 1/3 of the brownies. Scrunch that in. Okay, so can the brownie problem be solved? No. Explain, if not, explain why not. The reason is because we don't know if there's any overlap or not. We need that to be clarified for us. Is the brownie problem the picture we see in B? If so, explain why. If not, modify. And is the brownie problem the image we see in C? If not, modify. Okay, so we get no for all of these. And then for B, let's write ourselves a problem. B would look like, we have to modify this one. You're baking brownies for your class. You put white frosting on a third of the brownies and you put, so we're gonna start there. And you put small red hearts on the frosted brownies. Dot, dot, dot. So we've modified the word problem with this sentence here. We want to remove this statement and replace it with our statement so that it reads, you are baking brownies for your class. You put white frosting on 1/3 of the brownies, and you put small red hearts on the frosted brownies. How many brownies have both white frosting and small red hearts on them? Okay, now to get the image to be 1/3 plus 1/4, what should we modify? So for C, which we have above, so I'm going to write it actually up here to match the top drawing. So for 1/3 plus 1/4, we need to be sure to note that they're not frosted. So we're going to say, same place, I think we're going to cross this out and say, and you put small red hearts on the oh wait, I just noticed, and you put small red hearts on 1/4 of, right? We lost our fraction, on 1/4 of the frosted brownies. So let me fix this one. Okay, that's better. Oh, we don't know how many also. So that's another fix that we have to do for this one. What fraction of the brownies have both, right? What fraction of the brownies have both? Okay, because to fix it for C, let's see, let's start over. Sorry, I caught that, so I had to go fix it. But now B reads, you're baking brownies for your class. You put white frosting on 1/3 of the brownies, and you put small red hearts on 1/4 of the frosted brownies. What fraction of the brownies have both white frosting and small red hearts on them? So now I believe that's fixed. And for C, then let me look at our question. You put white frosting on 1/3 of the brownies, and you put red hearts on 1/4 of the brownies. Let's get no frosted brownies have red hearts, so they're separate. So I'm inserting that here. What fraction of the brownies have either white frosting or small red hearts on them? So we've separated them. There's no overlap, and we're going to add the parts together. So you're baking brownies for your class. You put white frosting on 1/3 of the brownies, and you put small red hearts on 1/4 of the brownies. No frosted brownies have red hearts. What fraction of the brownies have either white frosting or small red hearts on them? Write a word problem for 1.3 times 2.79. Use our definition of multiplication to explain why your problem is a multiplication problem. Solve your problem without using a calculator. Okay, so we're going to start with the form of the definition. So we have 1.3 groups and 2.79 items per group, units per group. And we need to ask a question for a total number of items, whatever these are, right? And what we have then, generally, we use weights or we'll use money, right? When we're looking at multiplying decimal numbers. So for example, we could have something like $2.79 per pound, right? Per pound. That would be then 1.3 pounds that we're buying. And we're asking then how much money are we spending, right? So as long as we set our question up to match this equation, we'll have explains why our problem fits the definition. So let's see. Cherries cost $2.79 per pound. And we get 1.3 pounds of cherries. How much money did we spend? And now they want us to multiply or solve the answer without using a calculator. Okay, so that means we're going to practice using the stacked algorithm and the uses of, well, we ignore the decimal places. So we treat these like whole numbers. And then we multiply as if they were whole numbers, right? So 3 times 9 is 27, right? 3 times 7 is 21, 23. 3 times 2 is 6, 7, 8. right? Show your carrying. Now we skip a space because we're in the 10 spots. We have 9, 7, 2, add straight down. 12, carry the 1. Actually carry it though. That was a hard carry. Let's see. Try that again. And then 15, 16, carry it. Carry the 1, gives me a 3. Now I went and multiplied by 10 3 times. Now I have to divide by 10 3 times. Okay, so going back, I'm going to put this in a smaller font for you. So we did times 10 to ignore the decimals, and we did times 10 to ignore the decimals. So to undo it, right, to get back to the actual place, but I'm a little close, we're going to divide by 10 3 times. And as a result, we can see our decimal place is at the 3.627 because we're going to divide by 10, divide by 10, divide by 10 to recover. Okay, so that's how we multiply in decimal form. The workings behind ignoring the decimals and treating the values as if they were whole numbers, and the process of recovering how many decimal places to put your decimal point when you return from this gigantic multiplication here. So in the end, you round to the cent location. So we spent $3.63 after rounding, but you will still want to show the answer before rounding, especially to prove you did it by hand, right? That type of thing. So solve your problem without using a calculator. Another way that we show the standard algorithm working, in addition to this side method here, we also do improper fractions, right? As a way of showing, let me write it down first, as a way of showing the ignoring the decimals and multiplying as if they were whole numbers part of the process when we multiply decimal numbers. Okay, so 1.3 times 2.79 is the same as 13 over 10 times 279 over 100, because we have 1.3 tenths, right? What, not 1.3 tenths, but 1 and 3 tenths. And we have 2 and 79 hundredths, right? So we have 13 tenths and 279 hundredths. All right, so now our standard algorithm for multiplying fractions says that we multiply 13 times 279, and then we will divide by 10 actually 3 times, where 100 itself is the quantity 10 times 10. So just like we saw in the stacked algorithm, when we ignore the decimal let's back up and restart it so that I can show both having the same actions. So at first, let's just stick a 1 under these numbers, because every number, right, can be thought of as implicitly over 1 and then be turned into a fraction form. So now we have these in fraction form, our first improper fraction. Now, to get the 1.3 to the form of a whole number, we're going to multiply the top by 10 as well as the bottom, right? And to get, to get the 2.79 to a whole number, we multiply by 10 twice, right? We're going to multiply by 100, which is 10 squared. And so we have 10 squared on the bottom as well. And then we get to the point where we have 13 times 279 on the top and 3 copies of the 10 in the bottom, right? Which often is just written 10 to the power 3. Okay, so now you can more clearly see when we wrote, let's write it, 2.79 times 1.3, we said multiply by 10 gets me to 279. Multiply 1.3 by 10 and we get to 13. And we can ignore the decimal places and multiply these as if they were whole numbers, right? And as a result, right, I'm going to use a calculator this time. We had 279 times 13. We had the answer 3627. And then we said, because we arrowed over to the right 3 times, we're going to arrow over to the left 3 times, moving our decimal place 3 places to the left at the 3.627. Now, in our improper fraction algorithm, we have a numerator of 3627. And we will be dividing by 10 to the power 3, which is 1000, getting us the exact result of 3.627. So these are 2 different methods showing that the standard algorithm, let me catch up, which we don't even discuss really, we just do it, right? The standard algorithm in words is to ignore the decimal places, multiply as if they were whole numbers, then count the number of places you ignored to insert the decimal point that many places to the left of the rightmost digit, right? But these are 2 different methods of showing that algorithm. One being improper fractions. So here's an improper fractions method. and the other being this stacked algorithm version, which is very similar to how we actually write it, right? When we write the multiplication, we just ignore, like literally ignore it, then count and put them back in. But because we're trying to illustrate what it is we're ignoring, right? Then we need to show why it is that we recover putting the decimal point three places to the left of last digit, right? So it shows there in that algorithm, and it shows here in this algorithm. But both methods show that the standard algorithm of ignoring the decimal points, multiplying as if they were whole numbers, and then counting the number of places to put your decimal point back into place, these two methods show why that works. All right. For each of the following problems, determine if it is a decimal multiplication problem. If so, use our definition of multiplication to explain why and write the corresponding equation. If not, write a new decimal multiplication problem that uses a similar context. Use our definition of multiplication to explain why it is a multiplication problem and write the corresponding equation. Okay, so if the concrete cost, let's look at the definition of multiplication first. That way we have a center. So we have the number of groups times the number of units in one group, and then the total number of units. So that's our anchor, right? That's our definition of multiplication. And for A, if concrete costs $89.95, so $89.95 per 1 cubic yard, then how much will 7.5 cubic yards cost? So this is definitely a decimal multiplication problem. So our answer is yes. This is 7.5 times 89.95. So it says, let's see, if so, use our definition to explain why. So we're doing that right under the definition and write the corresponding equation. So we've done that. Now for B, we have, let me switch the colors out. If 1.5 liters of a liquid weigh 1.1 kilograms, then how much does 1 liter of that liquid weigh? So they're asking us about something per one, not a total amount of item, right? So they're actually asking us a division question here, but let's put it together. So they have weight per liter. So kilograms per liter is here. And then they've multiplied by the number of liters. So we would have our 1.5 liters, which is our groups. And then we have a 1.1 kilogram. So what they're actually asking us here is 1.1 divide by 1.5. That's the question that they're asking us here. So we have no, this is right now a division problem, a decimal division problem. So they want us to write a new problem with similar wording so that it does ask an appropriate question. And then what would that equation look like? So if we were to change this one, then we would want to say something like the 1.1 kilograms is how much 1 liter weighs. How much does 1.5 liters weigh, right? So we would want to switch those two around. So if 1 liter of liquid weighs 1.1 kilograms, then how much does 1.5 liters of that liquid weigh? Now we have 1.5 groups, right? That's our liters times 1.1 kilograms per liter. That's our units per group. And now we are asking about the number of liters. No, sorry, kilograms. Okay. So we've fixed it. So here is our fixed answer for the blue. Otherwise, outside of the fix is the original answer. So no, it was originally a division problem that looked like the annotated equations off to the side. Now we have in part C, we have if a meter long piece of wire weighs 1.3 kilograms, then how much do 2.8 meters of that kind of wire weigh? So this looks promising. Let's see, we've got 1.3 kilograms per meter here. And we have 2.8 meters. And they're asking us how many kilograms, right? So here we have a yes. This is a decimal multiplication problem. And it is 2.8 times 1.3. Okay. Given that 1 inch is equivalent to 2.54 centimeters, what is the equivalent of 8.5 centimeters in inches? Okay, so let's fit this last one on here. They gave us a 2.54 centimeters per inch here, but then they gave us 8.5 centimeters. Oh, I should put the same abbreviation. 8.5 centimeters. And so they're asking us about this location here for the number of inches. And so, no, they've given us a division problem of 8.5 divided by 2.54. Right, so that's what they've given us. So our answer is no, right? If they ask us a yes or no question, we have to say yes or no, and then we have to fix it, right? And so we would or could switch the number of inches and centimeters, right? Because if they gave us inches and asked for centimeters, that would be a good fix, right? So the words I added are my fix for part D. And now that I've fixed it, we would have 8.5 inches times 2.54 centimeters per inch. And we would then be asking for the amount of centimeters. So we've used the definitional multiplication to identify when we had decimal multiplication and when we didn't.